Great, it's recording now. Review for the final exam today. I'm gonna go in order as usual, right? But in case you want me to go over a specific question, let me know, remind me, and then I will mark that question. We will go over that for sure. We will not skip it, right? But the idea is to cover the main forms. Some questions are very similar, so I may say similar. But if you feel like I should still go over that, just let me know. Okay, guys, question number 1 deals with limits. They are asking you here to compute the limit of this function f of x, whose graph you see it on the left, right? As x approaches -1, as x approaches -1, right? First, and then they want you to compute the evaluation of this function at -1. Okay. Remember, the limit doesn't deal with what happens necessarily at the input value, in this case, -1, right? It deals with what happens on the neighborhood of -1, right? On the neighborhood. So when you deal with limits, it is always a good idea to approach from the left and from the right and see if there is convergence, right, on the output value. So if you approach, for example, from the left to this -1, you can see that the output values are headed here, right? Are headed here, this value. And if you approach from the right to -1, the output values are coming down to this output value here. Right? But what is that output value? Well, you see here, they give you that information, right? They say the partner of -1 in the graph here, the partner is 4/5. They're giving you this information. So write it there, 4/5. So from the left, the output values are going to 4/5. From the right, the output values are going to 4/5. Therefore, the limit of this function as x approaches -1 has to be 4/5, right? 4/5. Very good, guys. 4/5. Now, here, now they want you to evaluate the function at -1. For that, be careful there. Notice there is a hollow circle here. So the evaluation cannot be gotten there. Instead, look down here. You see a solid circle, right? This tells you the evaluation of -1 via this function, right? Evaluation of -1 is this guy, and clearly that guy is just -1. All right, guys, so I hope this is clear. It's a nice exercise. And when you choose your answer, be careful. First, you have to show the limit, then the evaluation. So first 4/5, then -1, right? Be careful there, guys, because look, this is very similar. It's just first the evaluation, then the limit. Be careful there, okay? Yeah, so that's the first question. Welcome all you guys who just joined. I think Oscar, Adriana, CG. Welcome all you guys. We are going over the review for the final. As usual, I'm going in order, but if I skip and you feel like I should go over a question that I am not considering, let me know. I will do it. Next question. Next question deals with computation of the limit. Hello, she great. I'm doing well, thank you. Yeah, so using tables, right? Using tables, okay? So for that, they have done the computations here and here, but the computations here and here, you have to do them. And then you have to figure out if there is convergence approaching from the left and from the right output-wise, right? Yeah, that's the idea. So what you're gonna do is you're gonna take your calculator, right? We're gonna do it quickly. Take this function, sine of a times x, but x is gonna be this from the left, right? 0.001. Gonna complete this table. Close parentheses carefully. All that divided by the input value -0.001. Now make sure that you are computing this in radians, right? Not in degrees, in radians, right? So change it to radians and see what you get there. Very good. Okay, so I'm getting this 7.99991, right? Very good. Let's see what I'm going to get if I evaluate now my function at an input value very, very close to the 0, right? 0. So I choose this input value from the table. I'm gonna just remove the negative signs there. And I see this value, right? Yeah. So therefore, right, writing this out here on the table, what number do you think we approach from the left, from the right? Anybody? From here, from here.
8.
8, right? Yeah. It will be clear what number you approach, right? It has to be clear from the left and from the right. We're approaching 8, right? So this limit therefore has to be equal to 8. Now, guys, at this time, we are taking our final, we're closing everything, right? We have to put together everything we have gotten during this semester, right? Some students, when I do this, professor, there's a pattern. Always when I do this exercise, the number that appears here ends up being here. True, guys. For this form, the number that appears here is important because it's precisely the limit. It's precisely the limit, right? Now, I'm not saying that this is going to be always the case, right? Let's say, for example, they put the number 2 on the bottom, then will be the half, right? But if this is the form, sine of k times x over x, and I even give you a property, right? This number, very important, right? Yeah, very good. So important to catch patterns. Very good. So here is the answer. Moving on. They want you to compute this limit now algebraically. Okay, and we explained that for that, you should always try direct evaluation first, right? No matter what. Why you say that, Professor? Well, what if it works? What if your direct evaluation works? Well, if it works, then you're done. So it's always worth it to try. So if you try here direct evaluation, notice this is going to be 9 minus 9 is 0 minus 1. You end up with -1, a real number, right? So it is the limit of this function, right? And the reason why this works is because this quadratic function, whose graph is a parabola, is continuous all the time, right? But there is continuity. It is enough to do direct evaluation to get a limit. Excellent. Now, however, this direct evaluation in some cases does not work. For example, in this number 4, when you compute the limit, if you plug 3 into this function, you're going to get this on the numerator. You're going to get this on the denominator, right? Yeah. 3 squared is 9. 9 minus 9, 0. 3 squared is 9. 9, this is 12. 9 minus 12, minus 3. Minus 3 plus 3, 0. 0 over 0, Professor. Undefined. Yeah, but that doesn't mean that the limit that we have here is undefined. All it means is that we should try some other approach, right, to overcome this undefined situation, right? And I have given you techniques to do that. So if this happens, then one technique is called factorization, factor, numerator and denominator. So you should get this. X squared minus 9 factors as x minus 3 times x plus 3, right? Over here, we look for two numbers whose multiplication is 3, whose sum is -4. After some trial and error, you will end up with 3 and 1. The sum, you want it to be -4, so this has to be negative, this has to be negative, right? Now, once you factor, this reveals something. Notice that x minus 3 and x minus 3 can be canceled. So it reveals or shows that the function that they gave you here is really this one in disguise, right? It's still a rational function, but simpler, and better behave. Professor, why you say better behave? Well, in the following sense. Now, if I do direct evaluation, it will not give me trouble. Look, 3 plus 3 here, 3 minus 1 here, 3 plus 3 is 6, 3 minus 1 is 2. So this should be S3, right? Very good. And that's the answer, right? So don't go for this factor, overcome this difficulty, and then your limit will come out there. Okay, very good, guys, very good. Moving on. Another form, the one with radicals. Again, if you start by just plugging the value into, notice we are going to encounter trouble here. Look, 1 plus 0 is 1, square root of 1, 1, minus 1 is 1 minus 1 is 0. Here, 0, 0 over 0, professor. Yeah, that doesn't mean that you have to go for this, right? Be careful, guys. Try some strategies that we cover during the lectures to overcome this difficulty, right? So one strategy that I suggested for this form was to multiply top and bottom of this by the conjugate of the numerator, right? Professor, why you are multiplying by the conjugate of the numerator? Well, because in the numerator is where the radical appears, right? Yeah, that's the idea. So multiply this by the conjugate. What is the conjugate? It's basically the same expression. The only thing that changes is the sign of the second term, right? The sign of this. So it's negative, here plus. This, the numerator and the denominator also, right? Plus 1. Okay. Now remember, you are going to work out the numerator, okay? But the denominator, you will leave it alone. What do you mean leave it alone, professor? Well, leave it in factor form like this, right? Do not expand. Do not expand. Just leave it like this. The numerator is the one that you work out. Look, a square root of 1 plus x times a square root of 1 plus x is a square root of 1 plus x, a square. The square will kill the radical, right? The radical. So it will come out like this. Now, this times this. This guy, 1 plus x. This times this, minus the square root of 1 plus x. Negative 1 times 1, negative 1. And here is something that always happens when you multiply a quantity by its conjugate. The middle terms, this second and third term, they always cancel because they come out to be opposite of each other. They go away. So cleaning this up, we're gonna stay with this, right? Limit as x approaches 0 of what? 1 minus 1, 0, right? 0. So this guy's cancel too. 1 and 1. Yeah, x is the only one left. And this is the reason why I ask you to keep the denominator in factor form. Notice here you can see that x and x can be canceled, right? Can be canceled. That's the reason, because if you expand, you're not going to notice that. These two cancel. And finally, we get a new function that is going to be better behaved than the original function. This compared to this, look. Why is better behaved, professor? Well, because now it will allow me to do the direct evaluation, right? So it's not going to give me trouble anymore. A square root of 1 plus 0, 1, a square root of 1, 1, 1 plus 1, 2, 1/2, this whole thing, right? 1/2. Very good, guys, 1/2. So that is here. Very good. Okay, so far so good. Let's move on. As you can see, we're trying to cover different forms. Another one here. This deals with limits that are called infinite limits, right? I'll remind you here. What if you get something like this and they ask you to take the limit? And they are saying, take the limit of 1 over x minus 5 squared as x approaches 5 from the left. How do you know, professor, that x approaches 5 from the left? Because of this negative sign on the top. This means approach 5 from the left. Okay, so for these forms, 1 over something squared, something cubed, something raised to 4 power. Remember, we explained that you have to look at the graph of this function, 1 over x squared. Remember the graph of 1 over x squared looks like a volcano, right? Like this. This is something that you should really remember, like this. Now, this graph, 1 over x minus 5 squared, is just a shift of this graph 5 units to the right, right? 5 units to the right. So I'm going to do it here. So this shift 2, 4, 5 will show a new volcano here, just shifted. But the trends are the same, right? So that's the whole idea. So this is y equal 1 over x minus 5 squared. Now they're saying approach 5, which is here, from the left. If you approach 5 from the left, the output values will go up, will grow without bound, right? Without bound, up, headed to what mathematicians call positive infinity, right? So the limit of this guy should be positive infinity or simply infinity, right? We are allowed to drop the positive sign, right? All right, guys, moving on. Moving on. This was infinite limit. What else we have? We have here a piecewise function. This deals with continuity, right? It says find the value for a so that the function f of x is continuous. This is a piecewise function, comes in two pieces, a quadratic piece, a parabola, and a cubic piece, like a chair. The idea is to figure out the value of x such that the parabola piece and the chair-like piece, they connect, they click, right? They click. And I gave you a nice technique here. I said, simply do this. Make sure that the limit of the function as x approaches, this is a key number, right? As x approaches -2, from the left is equal to the limit of the function as x approaches -2 from the right, right? From the right. So this is what you have to do to guarantee that they will connect. Now, this limit has to consider this function, right? Because if you are approaching -2 from the left, you are dealing with values of x that are less than -2. So you gotta use this guy. So the limit will be -2 evaluated at this formula, square plus -2 plus a, that's this limit. And the limit as x approaches -2 from the right has to consider this function, the cubic function, right? Why? Because this deals with values that are on the right of -2, right? So this should be -2 cubed. Here you have an equation that you can solve and figure out the value of a, right? This is 4 minus 2 is 2 plus a. This is -8, right? As usual, guys, if you have difficulties with this computation, you can use the calculator, right? Finally, a should be equal to -10. Very good. This will guarantee that these two, when graph, they will connect, right? So very good, very good. Number 7, that's it. All right, that was for continuity. Derivatives now. How do you know, Professor, is derivatives? Because of this, guys. Remember, this is how mathematicians say take the derivative of y with respect to x, right? They sometimes don't write it in words, they write it in symbol, dy with respect to x. Taking the derivative of this, taking the derivative of polynomials, easy, right? So let's use this notation. Y prime will be equal to what? Derivative of this part, 10 coming down, multiplying 1/2, which is 5, x raised to 1 less, 9, minus 5 comes down, divided by 5 is just 1, x raised to the 4th power. I hope everybody is okay with this. So we are talking about this guy, right? For number 8. Yeah, very good, very good. Yeah, so far so good. Now, this was for the derivative of polynomials. Now, let's talk about finding the slope of a curve at the point indicated. They give you this function. They want you to figure out the slope of the curve, the slope of the tangent line, right? That's what they mean. When x is equal to 4. For that, remember, compute the derivative, because we know that the derivative controls the slope of the tangent line, right? Take this constant out, focus on taking a derivative of this guy. But we explained, right? that the derivative of the square root of x, all work out, all simplify, is this 1 over twice the square root of x. If you didn't memorize this, have this written out somewhere when you take the exam, right? It will help. All right, so the derivative is just this 1 over twice square root of x, right? Simplifying, this becomes 4 over square root of x. So this is the derivative, right? The derivative, 4 over square root of x. But at x equal 4, then this gives me the slope of the tangent line, right? The slope of the tangent line will be what? 4 over the square root of x equal to 4. So this is 2. 2 into 4 is just 2, right? 2. Yeah, very good, guys. 9. This one, right? Yeah, great. Now this is similar, but they're giving you a polynomial. But now they don't want just the slope; they want the equation of the tangent line, right? The equation. So we gotta go a step farther. But it shouldn't be difficult because look, you take the derivative quickly. The derivative here is twice x minus 1. They want you to figure out the slope of the tangent line, right? For that, you use this value of x at x equal -3, right? First coordinate. What is this? Twice times -3 minus 1. This is -6 minus 1 minus 7, right? So it turns out that the derivative tells you that the slope of the tangent line is -7, right? Now, together with that, you have a point here. So with point and slope, not too hard to figure out the equation of the line, right? I use this slope point form because this allows extension later in calculus 2. You may use any method to figure this out, the equation of the tangent line. 12 y minus 12 equals slope minus 7 times x minus 3. Be careful with the signs, guys, there. Yeah, you will have 4 hours for your exam, so do things slowly, right? But safely. Yeah, 7x. This is plus 3. Plus 3 times -7 minus 21, right? Plus 12, y equal minus 7x. This is just -9, right? -9. So we are talking about this, right? Very good, very good. Yeah, so this one now deals with the derivative of the product of two functions, the multiplication of two functions, right? Product. So we require then to use this so-called product rule, right? Product rule. Derivative of f times g, f prime times g plus g prime times f. Call this guy f, call this guy g. Proceed, right? Derivative will be derivative of f is -6x times the other function as it is, right? No derivative, plus derivative of g, now derivative of this function, 2 comes down, multiplies by 10x times f, the function f as it is, 5 minus 3x squared. Now you see that on the choices, all the answers are in expanded form, right? So let's just expand this. Careful, right? -6 minus 5 minus 30 x cubed -6 minus 60 minus a minus plus. This is 36 at a 0 there, x, right? Yeah, this one 50x. And again, guys, if you need a calculator, you can use it, right? Minus 30x cubed. Now, combine like terms, right? Combine like terms if possible. So these two are like terms. -30 minus 30 minus 60. Attach the variable part. Variable part stays the same. And here 360 plus 50, 410, right? 410x. Yeah. Very good, guys. Very good. So 11 should be the first one, this one, right? Yeah, look carefully, -60x cubed plus 410x. Very good. That was an application of the product rule. Now let's look at the application of the quotient rule. Sometimes they will give you quotients such as this, f over g, right? For that, you gotta recall this quotient rule, which goes like this: f prime times g minus g prime times f over g squared, right? It's a quotient rule. So let's use the quotient rule there. So the derivative will be derivative of the numerator. Derivative of the numerator is just 1 times g x minus 2, right? As it is, minus the derivative of g. Derivative of g is 1 times function f is x plus 2 all over x minus 2 squared, right? X minus 2 squared. Do the algebra here, simplify, guys, and that should be it, right? 1 times x is just x. 1 times negative 2 is negative 2. Negative 1 times x, negative x. Negative 1 times positive 2, negative 2. Now, notice that x and x, they cancel. X minus x, 0. However, negative 2 minus 2, that is 4, negative, right? Negative 4. So negative 4, x minus 2 squared. Excellent, that's it. Now, look through and you will see your answer there, right? You will see your answer there. This guy. Yeah, be careful. Choices close, very close to each other, right? Be careful. Now let's talk about second derivative. At a certain point, they will ask you to get the second derivative of some functions. The function in this case is 3x times sine of x, right? It's the multiplication of two functions. So quickly identify the first factor with f, the second factor with g, and use your product rule, right? Product rule, this f prime g plus g prime f. Use your product rule. So y prime here should be equal to what? Derivative here, 3 times g sine of x plus derivative of sine. Anybody could tell us what is the derivative of sine?
Cosine.
Cosine, right? Cosine, excellent, right? Yeah, very good. Cosine of x times the other function f, 3x, right? 3x. That is the first derivative. Now organize your first derivative, right? This will help you to take the second derivative. This will be this plus 3x multiplied by cosine of x, right? I just put this up front, this following. Now, they say, take the second derivative. Professor, how do you know it's second derivative? Look at this number 2, right? The number 2 is telling you second derivative is needed. Not a problem because I can just take the derivative of the derivative, right? So I'm going to take the derivative of this now. Derivative of this part, 3 constant comes out. Derivative of sine, as Adriana said, cosine, right? Here, you got to be careful. Here, you need again product rule, f, g. I'll apply product rule again. So this will be plus derivative of f, 3 times function g as it is, plus derivative of g, derivative of cosine. Anybody could tell me derivative of cosine?
Negative sign.
Negative sign. Very good, very good, very good, guys. I see you're sharp. Very good. You got to recall those results, right? It will help you on your final exam. Negative sign, right? Yeah, very good. And that must be multiplied by 3x. Excellent, excellent. Very good. So finally, the second derivative should be equal to 3 cosine of x plus 3 cosine of x minus 3x. I'm writing the simple stuff on front, complicated stuff following, right? Yeah, great. These two can be combined, right? 3 cosine plus 3 cosine, 6 cosine, right? Like terms, minus 3x sine of x. That's it. All right, then look through and you should find your answer there, right? Very good, guys, very good. Is this. 6 cosine minus 3x sine of x. Excellent. Now, we have to talk about using the first derivative and the second derivatives for application. in this case, to physics, for example, right? Physics. In physics, you deal with position function, velocity, acceleration. So it turns out the first derivative gives you the velocity, the second derivative gives you the acceleration, right? They are giving you here a position function, which is this, and they are asking you to figure out what is the body's speed and acceleration at the end of the time interval. You start at time 0, you end at time 2, right? So you gotta do this at this value, at t equal 2 seconds. All right, so to get the velocity, simply take the derivative of the position function. But what is that? Well, this is 6t plus 2, right? Plus 2, that's the derivative. This is the velocity. And then you say, right, at t equal 2, at t equal 2, the velocity evaluated at 2 should be 6 times 2 plus 2. That is 12 plus 2, 14. 14, right? 14. In the end, feel free to attach units, meters per second. That's the velocity. But they want the speed. I show you how to go from velocity to speed, right? You just take the absolute value of the velocity, whatever it is, positive or negative. The speed has to come out positive, right? Since this is my velocity, the speed will be just 14 meters per second. Great. Acceleration. Acceleration should be the derivative of the velocity, right? The derivative of this. Or equivalently, the second derivative of the position function, right? Either or. Okay, A will be the derivative of the velocity 6. 6 is a constant function, 6. In the end, feel free to attach your units, meters per square second, right? That's it. And therefore, you can answer your question is this, right? The velocity is 14 and the acceleration 6 meters per square second. Very good, guys. Yeah. Yeah, this form is a little bit different, so we should take a look at that. It says the driver of a car is traveling at 48 feet per second, suddenly applies the brakes. The position of the car is given by this position function, s equal 48t minus 3t squared, t seconds after the driver applies the brakes. How many seconds after the driver applies the brakes does the car come to a stop? All right. A diagram probably will help to understand what's going on here. This is a car. Suddenly the car applies the brakes. Apply brakes, right? Driver. And as a result of that, given it's called inertia, right, in physics, the car keeps moving, right, for a while, keeps moving, and then it stops. The car stops. Yeah, great. What I'm asking you is how long it took from the time the driver pushed the brakes till the time the car stopped, right? We're gonna figure this out. All right, for that, I'm going to compute first the velocity as the derivative of the position function, which is gonna be just 48 minus 6t, right? 6t, that's the velocity function. And then you have to think of this, right? The car will stop when the velocity is 0, right? When the velocity is 0. So because of that, you have to set your velocity that we found here equal to 0, and then solve for t. Solve for t, right? This will tell us at what time the car, or after how many seconds the car will stop, right? Better said. So set it equal to 0, solve for t. Minus 48 here, minus 48 here, minus 60 equal minus 48. Negative 6 into 48 is just 8. The negative signs, they cancel, right? So after 8 seconds, the car will stop, right? Follow, guys? Very good, very good. So that was question 15. Let's go over question 16. Find the derivative of this function, s equal t to the 5th power minus cosecant t plus 17, right? Derivatives of t to the 5th power, 5t to the 4. Anybody could tell me what's the derivative of cosecant? you can check your notes or your
Minus
your sheet.
cosecant cotangent.
It's very good, Adriana. You made my day. Minus cosecant of t times cotangent of t. Great, great, right? If you know this by heart, very good. But in case you say, I'm not sure, you know, I want to double check, not a problem, guys. Here I gave you this summary of formulas, right? Here you will find the derivatives and also the antiderivatives. And this formula for cosecant is here. Cosecant minus cosecant times cotangent, right? Very good. Yeah, it's there. Yeah, in case you don't have this, guys, I think I posted in our website, right? And there are useful links, I think, but if not, here it is. Great. Okay, now simplify. This will simplify to 5t to the 4th power plus cosecant of t, cotangent of t plus 17, right? Correct? So therefore, then you can find the answer there for 16 is this one, right? Very good. The derivative of 17 is 0. This one, derivative 0, right? So I shouldn't have written this one. Yeah.
Professor.
I guess, yeah, this one is
Okay.
not there. Yeah, because it's the derivative of the constant, right? Very good. Maybe I can put plus 0. Yeah, excellent, guys. That you are checking, right? Yeah, 0 here. Yeah, very good, very good. Excellent. Yeah, moving on. So now chain rule also the heart of calculus, right? How to take the derivative of this function using the chain rule. Now, guys, since we are, you know, putting all together, all our knowledge together, right? Now, use any tool that you can have, anything that helps. If it takes you to the answer, it's okay, right? In this particular example, they are asking you to use the first form of the derivative, right? Because remember that's dy dx equal dy du dx, right? But really, we have this other way to take the derivative sort of quicker, right? Is using the outside function, inside function, right? The composition of functions. And the chain rule in that form says, well, the derivative is this, the derivative of the outside function, which is this 6 times the inside function raised to the 5th power, right? Times the derivative of this inside function. Yeah, anybody could tell me what's the derivative of this inside function?
-3.
-3, excellent, right? Yeah, but and that's it. Now, you just look at your final result. Look, this is -18 times -3x plus 8 raised to the 5th power, right? Look through the choices for this guy. Yeah, and you will see that that guy appears here, right? Here. So this is it. Now you can double check, right? The change of variable is this always. U is always the inside, consistent with that, right? U is the inside. And u, if you call your inside function u, then y has to be u raised to the 6th power, right? So consistent with that. So this is it. Okay. Okay. Yeah, very good, guys. Moving on. We have to another case for the chain rule. Yeah, let's do it quickly. Yeah, we are good. I think, yeah, there's y prime. I am going to take again this as my outside function, this as my inside function. Derivative of cotangent turns out is minus cosecant squared, okay? So start with that. Derivative of cotangent minus cosecant squared, derivative of outside function of your inside function, 5x minus 7, times the derivative of your inside function. But the derivative of the inside function is just 5, right? 5. So this is it. And then look for the final answer there. Bring the number 5 up front, right? So that's it, right? That's it. So for number 18, we're talking about this because here, look, this is what we got, right? the change of variable u again inside function, and if that is true, then the y is this guy cosine of u, right? So everything good. Very good. Moving on. Then we have here some applications of the chain rule. Here, for example, they want you to use the chain rule twice. Chain rule twice, Professor? What do you mean? Well, notice that this function is this. Minus 18. The whole thing raised to a fifth power, right? Mathematicians put the power in the middle, but it's better to write it this way for us to see what is really going on here. Look, this is the outsidemost function, the fifth power function, right? Fifth power function. Inside that function, there is this inside function cosine of, and then there is another function here, another function there, right? So there are three functions there. So it's a nested composite function, right? So remember we said start with the outsidemost. So start with the derivative of the outsidemost function. So this will be equal to what? 5 times. One less stays here. So for power cosine of pi t minus 18, right? And then you have to multiply this by the derivative of this guy. But the derivative of this guy, for the derivative of this guy, you have to use your chain rule again, right? Because this is itself a composite function. You follow, guys? Yeah, so y prime will be equal to what? Y prime will be equal to 5. I'm going to put this in the middle for the purpose of presenting my final answer, right? Derivative of this. Remember, this is my outside function cosine. So start with that. Derivative of the outside function is negative sign. I'm going to place it within parentheses, or you can use brackets. Within brackets, I would write minus sign of this guy, pi t minus 18 times the derivative of the inside function now, which is just pi, right? Pi. Close your brackets here, and then just simplify this. I have pi here, I have 5 here, negative 1 here. Put them all together up front. So you will have this minus 5 multiplied by pi cosine raised to the 4th power of pi times t minus 18 multiplied by sine of pi times t minus 18, right? Minus 18, and that's it. Yeah, be careful there, guys. Application of the chain rule twice, right? So this gives us this guy. Very good. Another derivative using the chain rule. I think it's worth it if we make sure that everybody understands this form. It's a little bit tricky. I will explain. It's a product of two functions, right? But one of them is a composite function. So let's call this f. Let's call this g. Let's apply our product rule, which is this. Prime g plus g prime f. Start with the derivative of f is just the number 2. That multiplies g, which is 4x plus 2 raised to the 5th power, plus derivative of g. G is a composite function, so its derivative will be 5 times 4x plus 2 raised to 1 less 4 times the derivative of the inside function 4. That's just the derivative of g. You still have to multiply by f, which is twice x, right? Professor, I got my answer. Yeah, we did, right? We got the derivative, but notice that they somehow presented the answer here in some factor form. So how can we get that factor form? The advice was this, right? Try to look at whatever appears in both terms. For example, here I have 2 and 2, right? These two guys appear there in both. So mark them, and also look at the yeah. So we have this guy and this guy. Look at this power appears here, right? Here was 0.5, here was 0.4. So we're gonna factor that out twice. What? 4x plus 2. take the one with the smallest exponent. This is the way you compute what they call sometimes the greatest common factor, right? Then open parenthesis, close parenthesis. This guy into this guy, look, 2 into 2, 1. This guy into this guy is just this, 4x plus 2, right? Plus. This guy into this guy. 2 will cancel this 2. This guy will cancel this guy. What is left? 5 times 4, right? The only thing left. And I'll just simplify this part and we should be done. Y prime equals twice 4x plus 2 raised to the 4 power. 4x, this is 2. This is 5 times 4, 20. 20 plus 2, 22, right? 4x plus 22. Mm-hmm. Yeah, so I think I might have done something.
Professor, what about
okay, let's check, okay? Let's check like derivative of this 2 times this plus derivative of this 2 times the inside function times 2x. This x was there, right? This x should be there. Remember? Look, this guy into this whole thing eliminates this and 2, but 5 times 4 times x stays. So this is 20x. So let's be careful there, guys. 20x, right? 20x. So guys, when you simplify, you will be left with 4x plus 2 plus 20x, right? 20x. All right. And then finally, y prime equals twice 4x plus 2 raised to the 4 power. 4x plus 20x, 24x plus 2. This is good. All right, so look through there and you will find your answer in this special factor form, right? It's a special factor form because it's not a complete factorization, but it's something that allows you, for example, to solve for this equals 0. Many reasons mathematicians prefer factor form over expanded form, right? So just follow this, guys. There you go. All right, moving on. We did chain rule. I think we are good with chain rule. Another for chain rule here, this one deals with inverse trigonometric functions. Yeah, let's do this. Yeah, I think we are good. Derivative. Number 2 constant comes out. We're going to focus on the derivative of sine inverse, right? But this sine inverse is a composite function. Derivative of sine inverse, remember, derivative of this sine inverse, you have this on your sheets. The derivative of this guy is 1 over 1 minus x squared, right? This is what we have. So use that. So it's going to be sine, the derivative of sine inverse, I'm going to take it directly, okay? So derivative of this, once you put the 2 outside, will be 1 over square root of 1 minus something squared. But what is that something? Is this inside function, right? 4x cubed inside. Times the derivative of the inside function. Derivative of the inside function, 3 coming down, multiplying 4, 12x squared. And what is left is just to put all this together this way. 12 times 2, 24, x squared on the top, on the bottom, this guy, right? Square root of 1 minus 4 squared, 16, x cubed squared, multiplying the exponents, x to the 6. And that's it, right? That's it. You will see it there. I think it's this one. Very good. Very good. We reached this part which deals with which is called implicit differentiation, right? Implicit differentiation. X to the 5th equal cotangent of y. Figure out the derivative of y with respect to x. For that, I gave you this nice technique. Take the derivative with respect to x of both sides of the equation, right? Very good. Derivative of this guy is just 5x to the 4. But derivative of this is equal to what? Derivative of cotangent is minus cosecant square of y. But since we are taking the derivative with respect to x, we have to attach dy dx, right? That's it. Now isolate this guy, isolate the guy. To isolate that guy, simply divide both sides of your equation by whatever is next to what you want to isolate, right? This minus cosecant square of y, this cancels, and this is it. So dy dx using implicit differentiation 5x to the 4 divided by minus cosecant square of y. Look through, it should be there. Very good, very good. Another one here, another one for implicit differentiation, but this one deals with figuring out the equation of the tangent line, right? At some given point of this curve, right? The one represented by this equation. It's a curve. So this is the point, 0, 1. This is x, this is y. Okay. And I gave you a nice technique. I said, okay, take derivatives in both sides first. And then rather than isolating dy dx, directly substitute the values here, right? Look, derivative of y to the fifth, 5y to the 4th power dy dx, right? Plus derivative of this guy, 3x squared. Derivative of this guy, 2y. The derivative comes to mind, but we're going to attach dy dx, right? Plus derivative of this guy, 9. Right there, substitute x with 0, y with 1. That way, we will find quickly the slope of our tangent line, which is this, right? That I can represent with the letter m. M. X is 0, 0 squared, twice y, y is 1, you can see, right? M again, plus 9. Now this is 5m. This disappears, 0, 2m plus 9. Subtracting 2m in both sides, I get 3m equal 9. Dividing both sides by 3m equal 3, right? I found this slope. The slope together with this point, right, should give you the equation, right? So x1, y1. So you do y minus y1 equal a slope times x minus x1. And you will see that this is going to lead to the following. This disappears, adding 1 to both sides. Once you remove this, y equal 3x plus 1, right? 3x plus 1. All right, so this is this guy. That was for 23. Yeah, very good. Yeah, moving on. This one requires the quotient rule, but I think we did the quotient rule, so probably this you can do it on your own. Perhaps I should do this, okay? This is similar. Let's do this, and then we will take the first break. Suppose they want you to figure out the equation of line tangent to this curve at this point, a equals 0. The curve is this, so quickly I find the derivative, which is going to be e raised to ax times the derivative of the inside function 8, right? And this derivative at x equals 0, why equals x equals 0, professor? Because of this, right? They're saying at a equals 0. It will give me the slope of the tangent line to be equal to this, e raised to 8 times 0, right? Times 8. 8 times 0 is 0. E to the 0 is 1. This is 1. You can check on your calculator. So the whole computation, 8. The slope is 8. The slope 8.0, comma. Professor, they didn't give me the y value. Not a problem, because the y value can be gotten by substituting the x value into the original function, right? This way. So a slope 8. This is 0 again, e to the 0, 1. So it will be y minus y1, a slope x minus x1. Do this, guys, the way you feel comfortable doing this. Y minus 1 equal a slope 8x minus 0. Again, this disappears, 8x here, adding 1 to both sides, y equal 8x plus 1, right? 8x plus 1, this guy. Says that the ladder problem, right? The ladder problem. Remember, there's a ladder that is falling in this direction at this speed. The ladder is 15 feet long. It's falling at some speed 2 feet per second, right? And they are asking you to figure out what is the speed of this point, right? When the bottom is 12 feet from the wall, right? So remember, if you measure the horizontal distance with X, the vertical distance with Y, at any time, this is true, right? Because of the theorem of Pythagoras. We saw this in our lectures. Now, if you take derivatives in both sides, what you get, and the derivative must be taken with respect to time, remember, right? For rate rates, you get this, twice x dx dt here, plus twice y dy dt, equal derivative of constant 0, right? 0. Now it's time to substitute what we have and find out what we don't have. X, do we have x? Well, they say that they want x to be 12 feet from the wall, right? So x is equal to 12. Good. Now, dx dt, this is what actually they want you to find out, right? The velocity of this point. Plus twice y. What is y? Well, I know that this is 12. That this is 12, right? And this is 15. So y can be computed as the square root of 15 squared minus 12 squared, right? Using the theorem of Pythagoras, right? And that must be multiplied by dy dt. Now, dy dt, guys, what is this? They say that this guy is falling at 2 feet per second. Question for you. Shall I write here -2 or +2? Anybody?
-2.
-2. Excellent, right? Negative because y is decreasing over time, right? Decreasing because of that negative. Be careful with the sign, guys, there. Okay. Yeah, and then the rest is just to solve for this guy, right? You get 24 here, dx dt. Here you get twice this whole thing. I think it's exact. It's I think it's 9, but again, guys, always play safe, right? For computations, especially if you're taking your final, right? You know, the mind is good, right? But sometimes, you know, it's better to double check. I said the thing is 9. It is 9, right? Very good. This is 9 times -2. -2. And from here, you can get this done. This is going to be 18 times 2, 36. If you transpose it to the other side, you get this, right? And from there, this will come out, 36. Dx dt will be the quotient, right? 24 into 36. That quotient is this 36 divided by 24, 1.5, 1.5. Positive, right? Positive, consistent with the fact that this guy is increasing over time. So 1.5 feet per second. Very good. Follow, guys? Okay. Yeah, what was number 28? Number 29 deals with the situation with water falling on a surface, and as a result, there is this circular shape that is being formed within a circular area that is expanding at this rate. How fast is the radius of the wetted area expanding when the radius is 159 millimeters? Remember, area equal pi r squared. If you don't remember this formula, write it down. That's the formula for the area of a circle in terms of the radius, right? And then if you take derivatives both sides with respect to time, what you're gonna get is this: derivative of the area with respect to time equal pi is a constant, comes out. Derivative of r squared is 2r dr dt, because we are taking the derivative with respect to time, right? Time to substitute what we have trying to find out what we don't have. We have the rate of change of the area, right? They say this is happening at 2 square millimeters per second. Positive because it's expanding. Pi times 2 times the radius they say is 159 millimeters. And the only quantity that is unknown is this. Divide this into this, and then you should get the answer, right? So take the calculator, 2 divided by what? Pi times 2 times 159. 0.002, right? 0.002. Rounded, following the instructions here, and this is just this guy, right? Very good, guys. So this guy, 0.0020. In the end, you may attach the units millimeters per second, right? Very good. Excellent. Now we reach to this part, linearization. Linearization, remember, is a way to approximate a function, which in this case is this, using the equation of a line, right? The equation of a line. And the linearization has a formula. The formula is this: f evaluated at the base point, which is pi in this case, plus the derivative evaluated at the base point, multiplied by x minus the base point. So let's do that. Evaluation of this at pi. What's the evaluation of the function tangent of pi? Tangent of pi, right? Tangent of pi. Let's write it directly there. Plus derivative. Derivative of tangent function is secant square, right? Secant square of what? Of pi. X minus our base point pi. Let's work this out. Tangent of pi, since tangent of pi is sine of pi over cosine of pi, is just 0. You can check this on your calculator. Tangent of pi, 0. Secant of pi is 1 over cosine of pi. Cosine of pi is -1. -1 squared is 1. You can check this on your calculator using cosine also, right? So leads to this. And then the linearization ends up being just this. X minus pi. Yeah, you don't know, guys. X minus pi is the equation of a line that serves to approximate this curve locally, right, around pi. Very good, very good. So this is good. Now let's talk about differentials. Differentials, remember, we talk about these differentials. They serve to deal with the small changes on the input values, right? This is the function that relates the volume with the radius, and they say by approximately how much does the volume of the sphere increase when the radius is increased by or from 1.0 centimeters to 1.1 centimeters. Use 3.14 for pi. All right, so first we take the differentials, right? Remember, the differentials go like this. Differential of v equal, you take the derivative here. The derivative of this is 4/3 pi. 3 comes down. And here r is square, right? That's the derivative. And then you write here dr. This is the relationship between the differential of the volume, differential of the radius. Now, notice we can cancel this guy, simplify this to this. Time to substitute what we have, time to get what we don't have. They want this dV, right? The variation on the volume. For pi, pi is 3.14. They are telling you to substitute this pi. Explicitly they're saying, right, substitute this by 3.14. R squared, what is R? For R, remember, in our lectures, we agreed that you always place the first value of R that you see there, the initial value of R, right? 1.0 must be squared. And the differential of the radius, is what? This difference of these two guys, right? So it's going to be the last one minus the first one. Yeah. Now compute this, and this is it. This is it, right? So take your calculator, right there, 4 times 3.14, close parenthesis here, open parenthesis again, 1.0 squared. Professor, that's just 1. I know, guys, I know, but the thing is that If it's not 1, it's 1.3, some other number, right? This is what you gotta do in general, guys, right? In general. All right, so I get 1.256, right? Look through, follow the directions for the rounding, right? You can see that they have rounded to 1 decimal place, right? So go for the closest. What is the closest? 1.3, right? Be careful, guys. Look, if you round it to 1 decimal place, 1.3, right? 1.3, no 1.2, 1.1, 1.3, 431, right? Yeah, excellent. 1.3, rounded, right? Great. In the end, you may attach units, right? Great. Now this is, we reached to this point where we have to talk about critical points. 32 deals with critical points. Let's find the critical points of this function. To set or to find the critical points, remember there is this method, set the derivative equal to 0, solve for x, right? We are gonna do that. Solve for x. Okay. Derivative of this function is 3x squared minus 18x, derivative of 90 equal to 0, right? And now we gotta solve for x. Factoring out 3x into 3x squared is x, minus 3x into 18x is 6, gives me this. Divided by 3 both sides, this guy disappears. X times x minus 6 equals 0. From there, x equals 0, first critical point. Second critical point comes from here, x equals 6, right? So that's it. 0 and 6 for 32. Okay, so yeah, we're good to go there. 0 and 6, this guy. Very good. Number 33 goes a step further. They say find the maximum, the absolute maximum, the absolute minimum for this function over this interval, right? So we start by setting our derivative equal to 0, and then we solve for x, right? To find our critical points as we did before, right? So 3x squared minus 12 equals 0, right? Factor out 3x squared minus 4 here. Factor this difference of squares as this, right? And then don't worry about this guy, disappears. Focus on these two. X minus 2 equals 0 leads to x equal 2. X plus 2 equals 0 leads to x equals minus 2. I got two critical points. Those two critical points should be considered for evaluations together with these endpoints, which are also critical points, right? We talk about that. These endpoints, formally speaking, should be considered also as critical points because the derivative there does not exist, so negative 2 and 2. So you're gonna do this, x here, f of x here, you're gonna do evaluations at these 4 values, right? 4 values. If you do the evaluations, take the calculator, right? And work efficiently there. We're gonna use this original function. So we're gonna do, the first evaluation should be what? Negative 3. Negative 3 is cube, right? Minus 12 times negative 3. Plus 5. First evaluation, I get 14. For the second evaluation, guys, if you work efficiently here, just copy and paste this and just change the input value, right, to negative 2 now. Yeah, so 21 now, right? Next, again, let's change this for negative 2, the third evaluation, right? You're gonna see the collection of outputs there that we have to compare, right? Yeah, we did this, now positive 2 in the next. Yep, great. And the last evaluation should be at 5, right? At 5. So let's put 5 there instead of negative 3. Great, right? I have all the evaluations there, right? So comparing, clearly, look, 14, 21 minus 11, 70. The largest is this one, right? And the smallest is this negative 11, right? Smallest, largest, so minimum, maximum. That's it. Very good, guys. So this was 14, this was 11, no, this was 21, sorry, 21 minus 11, and this was 70. This is the maximum, absolute maximum. This is absolute minimum, right? With this, guys, putting everything together, critical points are all these guys, and maximum value 70, minimum value 11. Okay. Great. Moving on. This one we briefly will discuss because we have checked this or done this in details in our lectures, right? You can check that. They just want to figure out where the function is increasing, where the function is decreasing. For that, I gave you this hint, right? Walk along the graph from left to right. Here increasing, right? Increasing. Decreasing here. You can see, right? Decreasing. And increasing again, right? Increasing. Whatever the shape of the graph is, walk from left to right, trace the graph, and this will tell you, right? With this, together with the following, look, notice that at this point, there is a local max. Why you say local max? Professor, it's not an absolute max, there is a higher output value here, right? Local max. This one, however, should be the absolute max, right? Absolute max. These two on the bottom, are local minimum here, but since they're the lowest of all output values, they should be absolute minimum, absolute mean, right? Two absolute means. Putting all this information together on 34, you will figure out that this is the answer, right? Look at the intervals, where it's increasing, where it's decreasing, and where you got the absolute minimum, absolute maximum. Great. This one deals with figuring out where the function is increasing or decreasing, but without looking at the graph. They don't give you a graph, right? They give you just this function, and you have to use the derivatives, to be precise, the sign of the derivatives to figure that out, right? So we gave out the method that says that to investigate where the function is increasing or decreasing, first take the derivative and find your critical point, right? For that, you are supposed to set your derivative equal to 0 and solve for c, right? Solve for c. So 27 minus 3z squared equals 0. I'm gonna just transpose this to the other side. There are different ways to solve these equations, guys. If you prefer factorization, you can try that too. I'm just, for the sake of variety, I'm used to doing this. I think it's easier. It's 9. Now, when you take the square root, be careful there. Is plus minus the square root of 9, right? Remember, when this is even, you have to use plus minus. So z, as in zebra, is -9. Z is equal to 9. These are the critical points, right? The critical points. Those critical points must be placed or set on the number line. Negative, actually 3 and 3, right? 3 here. 3. We're taking the square root. So square root of 9, 3, right? So -3 plus 3. So -3 here plus 3 here will subdivide your number line into 3 regions, 3 sub-intervals. You gotta check the signs of the derivative here. Okay, start here. For that, remember, you use test points. I can try the test point 4, evaluate that test point on your derivative, right? On your derivative. And you will realize that this test point is going to give you, as a result, when you put this 4 into this function, right? What do you get? This is the derivative, right? 4 squared is 16 times 3, 48. 48 minus 27. You can compute this in your calculator, right? Yes, let's do 27. Second. Mm-hmm. 27 minus 3 4 squared. minus 21, right? It's a negative number. So minus 21 tells you that this is all negative. We go to the middle, choose conveniently 0, easy to evaluate 0 on any function, right? This h at 0 is just 27, right? Positive now, positive here, right? And then over here, we're gonna choose negative 4. Negative 4 squared is the same as 4 squared, so it's gonna give us the same answer, minus 21, right? This is minus 21 negative, so this whole thing negative. So then this is telling us that this function is decreasing here, increasing here, and decreasing here, right? Decreasing here. Putting all that together there, it will be decreasing from minus infinity to negative 3, and also from 3 to infinity, right? And increasing from negative 3 to 3. So putting that all together on 35, you should get this, right? Very good. Okay, guys, moving on. This was for increasing, decreasing, using the derivative. Yeah, this 136 should be similar, right? So I will just take the derivative, analyze the signs, right? Let's move to some other topic. Let's check this out. 37. Find the extreme values of the function and where they occur. Extreme values. For the extreme values, remember, you have to take the derivative, set it equal to 0, and that will tell you, right? So quickly here, take the derivative. That is 3x squared minus 12, right? Set your derivative equal to 0 to find your critical points, right? So 3x squared minus 12 equals 0. Transpose this to the other side, changing its sign, right? Or adding 12 is the same thing. Divide both sides of this by 3. This gives you 4. X will be equal to plus minus the square root of 4. So this is telling you that x is equal to 2 negative and x is equal to 2 positive, right? There are 2 critical points. Set your critical points on your number line. These critical points are going to subdivide your number line into subintervals. And then figure out the signs of your derivative here. Take test points, cleverly choose good test points. For example, 3 will be a good test point here. The derivative evaluated at 3 is equal to what? This is my derivative function, right? If you put 3 here, look, 3 squared is 9. 9 times 3, 27. 27 minus 12 is just 15, right? Positive. Very good, positive there. Now, next here, I'm going to take my test point 0, derivative evaluated at 0, this derivative evaluated at 0, 0 here, minus 12, negative, right? This whole subinterval negative. Finally, over here, I take negative 3. Negative 3 squared is the same as 3 squared, so we're going to get the same output value here, minus 3. Should be 15, positive, right? Positive. Then basically this is saying that the function is increasing here, which I can represent like this, right? Increasing up to here, here at the critical point, derivative 0. So it has to decrease, decreasing here until I reach 2. And from there, increasing again, right? Something like this. It may look like this, right? But this serves for me to identify here a local max and a local mean here, right? Yeah, so the local max will be or will occur at negative 2 and will have as its partner what? Negative 2 evaluated at the original function, right? The original function. That function is the one that you use to figure out the second coordinate, right? That is not given there. So this cubed minus 12 times negative 2 plus 2 plus 2 gives me 18, right? 18. And let's get the other one as well. The one we evaluated at 2 is this. So 18 was for the first one. For the second one, negative 14. negative 14, okay? So this one 18, and this one 2,14. Telling you that the answer should be this, right? Local maximum here, local minimum here. Very good, guys. So moving on. This one, again, similar idea as we did before, but now we are dealing with concavity, right? Concavity. Remember, concave up, happy face, concave down, frown face, remember, right? So you travel along the curve from left to right. Look, it's increasing, reaches this maximum, then decreasing, but this is frown face, right? Frown face. Round face, so concave down, concave down, concave down. Here, the concavity changes. Look, this resembles the mouth of a happy face, right? Remember? So this is concave up, up. And at the same time, know how to see that the peak of this mountain determines a local max. The bottom of this valley determines a local mean, right? Local mean. Putting all your information together, guys, for 38, you will figure out that this is the answer, right? Look, this is what is shown there. This is what it's saying. All right, moving on. 39. Here they're saying determine where the given function is concave up and where it is concave down, but without the graph, right? And remember, for concavity, we have to use the second derivative, right? The second derivative. First derivative for critical points, but second derivative for concavity. So let's take the first derivative. That would be this, right? 24x minus 1. Now, second derivative will be 6x plus 24, right? Plus 24. Great. Okay, now we are supposed to set our second derivative equal to 0 and solve for x, right? Solve for x. So setting this equal to 0 and solving for x, what do we get? 6x plus 24 equals 0. 6x equal negative 24. X dividing both sides by 6 equal minus 4, right? Minus 4. I got a special point is the critical point of the derivative, right? If you want to use the word critical point, right? But it's a special point that we must set on the number line. And in this number line, we should figure out the signs of the second derivative. Because turns out, guys, second derivative controls the curvature of the concavity, right? Yeah, very good. So use test points. For example, cleverly, I can choose the test point 0 here, 0. If I choose 0, the second derivative, evaluate at 0. Second derivative is here. Evaluate at 0 is 24, positive, right? So I start with a positive sign here. And over here, I can choose negative 5. Second derivative, evaluate the negative 5. Look, negative 5 times 6 is negative 30. Negative 30 plus 24, negative 6, right? Negative, so this guy is negative. So concave down here, concave down, concave up here, right? Concave up, right? Yeah. And this is what you have to say here, right? So for 39, this is going to be the answer. Look, concave up on negative 4 to infinity, right? Concave up, and concave down from negative infinity to negative 4, right? Follow, guys? All right, great. So this is concavity via the second derivative. This is another one here. Concavity theorem function up and concave down. Also find all inflection points. Inflection points. Yeah, let's figure this out together. Yeah, so here we have to find concavity, but also inflection points. For concavity, remember guys, take your second derivative, right? First derivative of this function g will be x to the third minus 3x squared. Second derivative will be 3x squared minus 6, right? Minus 6 x. Great. Good. Set your second derivative equal to 0. Solve for x, right? 3x squared minus 6x equals 0. Factor out 3x. You will get this, right? Equals 0. And from there, you can say that x equals 0 is one critical point, x minus 2 equals 0 leads to the second critical point of the derivative, x equals 2. So 0 and 2 will be the points that you have to set on the number line, right? 0 here in the middle, 2 somewhere here. The subintervals come up here. We gotta figure out the signs of this function in here, right? Over this subinterval. So start here. Perhaps you can choose test point 3. Evaluate your second derivative at 3. Notice the second derivative is this. At 3, this will be 18, 27. So positive, right? Positive. So this is what really matters, positive. Here we can choose the test point 1, g double prime at 1. This was positive. Let's see how it comes up. This is 6 times 1, 6. 3 minus 6, negative, right? Negative less than 0. Well, this is what really matters. Then for minus 1, this is 1. Negative 1 squared is 1 times 3, 3. 3 plus 6 is 9. So positive, right? Positive. So concave up here, up. Concave down here, concave up here, right? There is change of concavity at 0. So it means that we got an inflection point at 0. There is change of concavity at 2. It means that we got an inflection point at 2, right? Now 0 substituted into the original equation leads to 0 plus minus 0 plus 8, 8. So this will be our first inflection point. For the second inflection point, substituting 2 into this equation, let's do it with a calculator, right? So 1/4 of 2 to the 4th power minus 2 to the 3rd power plus 8. Let's see what comes up. 4. 2 leads to 4. So these are the points. So therefore, your answer should be this, right? Concave up here and here, concave down here. Inflection points are this. Very good, guys. Now, let's talk about using differentials to approximate this. How do you approximate this using, not differential, using linearization, right? The linearization. Remember, there is a formula. It says this is equal to f of a plus f prime of a. This is the equation of the linearization, right? It's this, x minus a. A is a base point. Now, question for you guys. What could be a good base point? Let A be what? What do you think we should take as our base point to compute this?
64.
64. The idea is to choose a number that is close to this, very close to either on the left, on the right, most of the time on the left, right, but some cases on the right, and then choose for the function kind of that you're going to be by looking at this, right, the square root of x, right? With this, we're going to figure this out quickly. Look, first, evaluation on your function. So we are talking about a square root of x. Evaluate that a, but a is 64, so square root of 64 plus derivative. The derivative of the square root function, remember, is this, right? 1 over twice the square root of x, but we have to evaluate this at our base point. Our base point 64. Here, x is the actual number that you are dealing with, right? for the computation minus your base point that is very close to this 64, right? Put all this in the calculator, guys. That should give you the answer. Square root of 64 is 8. 1 over twice 8 multiplied by this difference is just 0.25. This is it. So let's put this in the calculator. 8 plus 1 over twice 8. Come out of there and times 0.25. It gives you this approximated value. Follow the instructions for the rounding. They say rounded to 5 decimal places. Right? So clearly this one, right? 441. C. Very good, guys. So this guy, 8.01563. Excellent. That's it. This one is similar. So similar. You can do it at home. Let's move on. Let's look for different forms. We reached the mean value theorem. Mean value theorem deals with this situation, right? They give you a function and they will ask you to verify the conclusion of the mean value theorem, which is this f of b minus f of a over b minus a, right? Equal to the derivative evaluated at c, right? B minus A, yeah, this is it. So if you do this, guys, you have to do f at -2 minus f at -3 over -2 minus -3, right? And that should be equal to the derivative, which is twice x, but since you are evaluating at c, it will be 2c plus 3, right? Now, when you compute this, we can do it quickly, right? F at -2 will be what? -2 squared is 4. 4 minus 6 is -2 plus 4, 2, right? 2 minus evaluation at 3. -3 squared, 9 minus 9, 0. This is 4, right? 4. 4 here. Over this difference is just 1. This equal to 2c plus 3. This is -2 equal to c plus 3. Solving this, this is -5 over 2, right? -5 equal to c. C equal -5 over 2. And then you just have to make sure that this guy is inside here, which is, right? Because this is -2.5. -2.5, of course, is inside there. So you check and you go for this. Very good. That was for 43. Yeah, very good, guys. So moving on. Let's talk about the next. The next is similar, but the function is different. It's deals with natural log. I think we did this during the lecture. So I'm gonna say this similar, and probably I can do number 45. Let's do this 45. Again, the idea is to check or to verify the conclusion of the mean value theorem, which is this. Great. So let's do that. Evaluation at 25 is what? The evaluation at B. 25 into this is 3, right? 3. 3 plus 25, 28. 28, right? Minus. Evaluation at A, which is this, right? This is your A, this is your B. Evaluation at 3, 3 into this is 25, plus 3, 28. So 28 again. This one, 25 minus 3 equal derivative. Derivative of this function, when you write your function as this, the derivative will be just 1 minus 75 x raised to minus 2, but we are evaluating at c, so c raised to minus 2, right? Very good. So that's it. Now, this is 0, 28 minus 28 is 0, divided by 25 minus 3 is 0, so equal to 1 minus 75 over c squared. Move this over, do what you have to do there, right? 75 over c squared equal 1. Multiply both sides of this by c squared. You will get that after canceling these two, 75 equal this c squared times 1 c squared. Take square roots. C will be the square root of 75. But you know that 75 is 25 times 3, right? So C will be equal to the square root of 25, 5 multiplied by square root of 3. Now, just make sure that this guy is inside this, which is the case, I think, right? Because if you compute it, you will see 5 multiplied by a square root of 3 is 5.66 is inside, right? So it's good, checks. 8.66 is inside. So very good, very good. So that's it, right? For some reason, they wanted to show this in exact form. So you gotta look for the exact form. It's there, right? For 45. Very good, guys. So great. So that's 45. This with the mean value theorem. Now let's talk about limits at infinity, right? Limits at infinity. This is what we did last week. First question says, find the limit of 6x over x minus 14 as x approaches infinity. Remember, we have a shortcut there. We identify the largest exponent on the denominator, right? And that is going to help us, right? We divide by that largest power, right? Better said, on the denominator, both numerator and denominator. This leads to this limit as x approaches infinity of 6 over 1 minus 14 over x. Now, x is a very big number. It's approaching infinity, right? So in the limit, this part will go to 0, right? Think of dividing 1 million into 14. This basically 0. So this appears. What is left is 6 over 1 as a constant function. So the limit will be equal to 6. This got 46. Very good. This one is similar. I will leave this for you to do. Similar. This one's similar as well, right? We should pay attention to this one. This one says find the limit again as x approaches infinity, but this time one of the functions, the one on the numerator has degree 1 is linear, right? The one on the denominator has degree 2, it's quadratic. This is what we call bottom heavy, right? Bottom heavy. And for bottom heavy, you know what happens, right? Once you identify the largest exponent on the denominator, this guy will undo this one. You will see 2x plus 1 over x squared. Here 14x squared minus 7 over x squared. And the limit as x approaches infinity, right? This guy will become 2 over x, simplifying, right? This guy will become 1 over x squared. This guy will become 14, this 7 over x squared. Notice that in the limit, these two guys, they go to 0, right? Because x is a very big number. This also goes to 0. Conclusion, 0 over 14 minus 0. 0 over 14, 0, 0, right? Which is something that we expect for bottom heavy rational functions, right? Yeah, so 0. Very good. That's for 49. For 50, I think it's similar. So let's skip that one. Let's move on. Yeah, this one's similar. This one is similar as well. Yeah, if you have difficulties, let me know. Similar. This one is going to negative infinity, 52. Let's see if we can check that out. Yeah, similar, I think, is still, because still will cancel. Yeah, this one also similar, divide by the biggest exponent on the denominator, which is this guy, right? And since it's bottom heavy, this is going to lead to 0, right? 0. Yeah, you can check that out. Good. Yeah, getting closer and closer to the ones that we're really interested. This one with negative infinity, again, is equally heavy. So you will end up dividing these two, right? So answer should be this. Very good. 64, similar. This one similar. Yeah, this one similar. So let's see one that leads to infinity. This one is interesting. Yeah, sometimes you will encounter this top-heavy rational functions. I will show you how to deal with this. For this top-heavy rational function, notice if you apply the trig, right? The trig says, divide by the biggest power on the denominator, which happens to be x squared, right? So we're going to divide this by x squared, this by x squared. So as a consequence of that, we're going to get limit as x approaches negative infinity of what? X squared into 2x cubed, 2x plus x squared into 3x squared, 3. Here, x squared into x, 1 over x, simplifying, minus x squared into 6x minus 6. Now notice that in the limit, since x is a very negative number such as negative 1 million, this will go to 0, right? Go to 0. But this will not go to 0, right? Instead, that will go to 2 times negative infinity, right? You just plug this in there. This disappears, 0 minus 6 stays in the bottom. 2 times negative infinity is negative infinity. Negative infinity plus 3, negative infinity, right? These numbers are nothing compared to negative infinity. But however, when you divide, be careful, guys, negative into negative positive. So this will come up as positive infinity. Positive infinity, so we're talking about this, right? You follow, guys? Be careful there. All right, this one, top heavy, also similar, the one that we just did. Great. This one, foil this out, and it's similar, right? Similar, foiling this out. We reached to this part that deals with figuring out horizontal asymptotes. Let's do this and then we will take the second break, okay? So to find the horizontal asymptote, remember, all you gotta do is this. You take the limit of this function as x approaches plus minus infinity. If you get a real number, you're done. You got yourself your horizontal asymptote. If you get something like positive infinity or negative infinity, then it means that you don't have a horizontal asymptote, right? Clearly, the biggest power on the denominator is x. So I'm going to divide by x, numerator and denominator. So I will get the following. X into 2x is 2, minus x into 2, 2 over x. Here, x into x, 1, minus 3 over x. These guys clearly go to 0 on the limit because x is very negative or very positive, right? Huge numbers in absolute value. So this one 0. But 2 over 1 stays. 2 over 1 stays. So this is 2. Then it means that my horizontal asymptote will have as its equation y equal 2, right? 2. That's it. That's this guy. Yeah, and this is what we call equally heavy rational functions. Equally heavy rational functions, remember the summary, they lead to asymptotes once you divide the leading coefficients here, 2 over 1, 2, right? Sorry. Okay, great, guys. So moving on. We have here the following now. Yeah, this was good. Now we have another one here, similar, right? Just take the limit as x approaches plus minus infinity. If you get a number, you got your horizontal asymptote. If not, you say no horizontal asymptote. In this case, clearly this goes to 0, limit is 8, so this should be the answer, right? Yeah, here, here I think this is interesting because this is a top-heavy rational function. When you take the limit as x approaches plus or minus infinity of this function, you will realize that the limit is not going to exist. Why you say that, Professor? Well, notice that this is the largest power on the denominator. So if you divide by the largest power on the denominator, you will get here the limit as x approaches plus minus infinity of x plus 9 here, right? Minus 2 over x, over here 1 minus 2 over x. These two guys will go to 0, right? Because x is either a very negative number, very large positive number, right? So 0. But these guys will stay. This is not going to go to 0. So substituting this in there, you will get plus minus infinity plus 9 over 1. Plus and minus infinity will swallow up this 9, right? 9 is nothing for infinity. So this will be plus minus infinity divided by 1 plus minus infinity. This is not a real number, right? So then no horizontal asymptote, right? Only when you get a real number, you get a horizontal asymptote. Otherwise, you just say no horizontal asymptote, okay? Very good, guys. This one, similar, right? Similar, but this one is equally heavy, so you will end up dividing 6 and 3. 3 into 6 is 2, so the horizontal asymptote should be this, right? For 63. This one is boron heavy. Remember, boron heavy leads to asymptote y equals 0, right? Good. 65, equally heavy, so similar. This one, top heavy. Top heavy do not have horizontal asymptote. Top heavy because the exponent here, the degree is 4, degrees here 1, no horizontal asymptote for 66. Very good, guys. So now let's try to see. Finally, we reach to the last part, right? Yeah, see, I'm going to mute you. Yeah, great. Okay, now it says a carpenter is building a rectangular room with a fixed perimeter of 420 feet. What are the dimensions of the largest room that can be built? All right, always a diagram, guys, helps, right? Let's draw a rectangle there. And I'm going to choose this to be X, this to be Y, right? You can choose the other way around, doesn't matter. But what matters is that you follow this. They say that the rectangular room has to have a fixed perimeter of 420, right? So no matter what, 2x plus 2y must be 420. This is what it's called the constraint equation. Now the goal is to maximize area, right? Area. So which means that a equal x times y should be maximized. This is what we call the objective function, right? Now from here, not hard to see that if you transpose this over here, 2y equal 420 minus twice x, dividing by 2 both sides, we get that y should be equal to 210 minus x, right? This is what you replace in here, okay? And you get your area function in terms of one variable, right? And why we should do that, Professor? Well, because in Calculus 1, guys, we know how to maximize functions defined in one variable, right? Not in two variables. So this is the reason. Now, after you do this, you set your derivative equal to 0 and solve for x, right? This will be the last step. All right, so 210 minus 2x equals 0 leads to 210 equal twice x. dividing both sides by 2, 105, this, right? Now, once you have x, then your y can be found because the y is equal to this, 210 minus x, but x is 105. So then y has to be this difference, which is 105. So answer turns out, as we explained, right, when you deal with maximizing a rectangular shape, there are no walls, no restrictions. This turns out to be a square, right? Square whose side or whose side length is 105. So 105 feet by 105 feet, right? You follow it? So, and also we can compute the area now, right? By multiplying x times y. And this area is equal to the following. The following 105 times 105. 11,025. 11,025. In the end, guys, feel free to attach units, square feet for this, feet for this, feet for this, right? Feet. Follow? Sarah, now this is clear.
Yeah.
Now,
I thought the answer was A. I was checking. The answer is A.
no, the answer is B because it says 105 for x, right?
No, my brain is
105. Yeah, you follow? Now, Sarah, everything clear?
Yeah, it's
yeah.
clear. That was my God, but when I was checking the answer, I thought I saw it as A. That's why I marked it. Thank you.
Yeah, I have here B. So everything's okay, right? Yeah. Crystal clear? Very good. Excellent. Yeah, great. Okay, and this is similar, right? You can do it at home. Now let's go ahead with a cube. 69. Yesterday, I think I did one of these, but I will do it again, okay? They say from a piece of cardboard 20 inches by 20 inches square, corners are cut out so that the size can be folded up to make a box. What dimensions would yield a box of maximum volume? What is the maximum volume? Write your answer to the nearest tenth if necessary. Okay, guys, so you start with a square right here, cardboard, and from there you're gonna cut on the corners these little squares, and they're asking you to cut squares here. Let's call this X to measure how much we have to cut, right? X, X, X and X, 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 X. Then, since you're removing this from the corners, once you fold up what is left, the flaps, right? Not hard to see that you should be able to construct then a box, right? A box, which we are going to represent here, that box here. Now, turns out that box is going to look more or less like this, right? Must have a height of X, right? We discussed this on our lecture, right? The height, because this corresponds to when you fold this up, right? When you fold this up. When you fold this up. All right, so X here, and this, the width and the length should be what? They say that originally the material they give you is 20 inches here, right? You're removing X here, you're removing X, so you're left with 20 minus twice X here, right? Similarly here, 20 minus twice X, because this is also 20. Now with this, guys, you are going to form the box. The objective function should be the volume of this box, which is going to be the height times the width times the length, right? This X times 20 minus twice X times 20 minus twice X. This away. This is the volume of the box. This is what we have to maximize, right? Now, let's work this out, this volume, right? This is going to be X. Let's FOIL this up. FOIL this out. 20 times 20, 400. 20 times -2 minus 40x. minus 40x again, and this should be plus 4x squared, right? Plus 4x squared. Great. So this is this. X times what? 400 minus 80x. It's a combination of these two plus 4x squared, right? Great. Finally, multiply x over x times 4x squared, 4x cubed. I am organizing my polynomial function. Minus 80x squared plus 400x. You follow, guys? Yeah, 4x cubed minus 80x squared plus 400x. Now, this is what we have to maximize, right? Maximize. So we have to take the derivative, set that derivative equal to 0, and solve for x, right? Solve for x. So set b prime equal to 0, solve for x. So if you take the derivative, that will be 12 x squared minus 160x plus 400, right? 400. Set that equal to 0 and solve. Now, we're going to solve this using our quadratic formula, right? Remember how we did it in class, in the lectures, using the quadratic formula. So with A equal 12, B equal negative 60, this C 400, right? I'm going to do the computations directly, okay? This is going to give me two solutions, okay? And we'll analyze the solutions, right? Yeah, great. So using the quadratic formula, then we're going to get the following. Let's do that. Minus B, which is minus 160, right? Minus the square root, or square root of B squared minus 60, 160 squared, sorry, square minus 4AC, AC 12, C is minus B squared minus 4AC, 400 here. And all this divided by twice A, right? Twice A. Yeah, this is going to be one of the computations. Twice 12. Let's start with a plus one, okay? And then we'll do the minus one. This is the plus one, gives me 10. The one with minus gives me 3.3333, right? Let's write it down. Again, 10 and 3.33. The two candidates, right? Again, this one 10, the other one 3.33. Good. So this is giving me two candidates, 10 and 3.33, right? These two candidates, you must test them via evaluations, x here and the volume here, right? The volume function here, which is this. So we're going to test 10 and 3.33. If we test 10, you will see the following. 4 times 10 cubed, 10 cubed minus 80 times 10 square plus 400 times 10, right? 0, Professor, 0. I will explain to you why it's 0, okay? 0 there. And then the other one, so the other one is this 33 instead here. 3.33. 3.33. This one is meaningful, right? The other one was 0. So let's write it down. And then I will explain to you why this is 0. 0 here, 592.59 cubic inches here. This doesn't make sense. If you take too much, if you take 10 here, there is nothing left to build the box, right? That is why the volume ends up being 0. So carrying 10, not good. Carrying 3.33 will maximize the volume, right? And what's the maximum volume? This guy, this one, right? Maximum volume, maximum volume. Now, to go to the answer, you have to express the dimensions. X, we are saying, is 3.33, right? So compute this, 20 minus 2 times 20 minus 2 times minus 2 times 3.33. What is that? 13.34, right? 13.34 inches. 13.34 inches. And this one, since the base is a square, the same, right? 13.34 inches, telling us that the answer should be this one, right? 13.3 by 13.3 by 3.3 with a volume of 592.59 rounded 0.6. Very good, guys. So this is the one that deals with constructing a box, right? Very good, very good. Let's move on. Let's move on, guys. Let's talk. This is a similar one. Let's talk about this one, the barn problem. They are trying to construct this this fencing, right? So the farmer decides to make 3 identical pens with 144 feet of fence. The pens will be next to each other, sharing a fence, and will be up against the barn, right? So we don't need material here. The barn side needs no fence. They're trying to figure out what are the dimensions such that this area is maximized. Remember, let this be X, 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 this guy be Y. No matter what you do, Y plus 4X, right? Y plus 4X has to be equal to 144, right? That's the fencing material. And you're supposed to maximize your area, right? Goal, maximize area. Maximize area, which is X times Y. From here, no hard to see that Y equal 144 minus 4X, right? Subtracting 4X in both sides. Then you replace that in here into your area function, right? Getting this. Area will be equal to X times 144x minus 4x squared. This is your objective function. Now set your objective function equal to 0, solve for x. Setting this derivative, which is 144 minus 8x, the derivative, equal to 0, we get here that our function is supposed to be this, right? 144 equal 8x, x, a into 144. Let's see what we get. 18, right? 18. Once you have x, guys, then y can be found, right? Because y depends on x. This way, right? So quickly you can find there your y is this. Let's compute it. 144 minus 4 times 18. 72. 72, right? So this is telling us, guys, that x is 18 feet, y 72 feet. This is what they are asking you to figure out, right? So this should be 18 feet by 72 feet. Very good. That was the barn problem. This one is similar. You can do it at home. Now let's check this out. A couple of problems here. Yeah, this one, I think we did this in the lecture, right? So I think you will be okay with this. With this apply to finance. Let's look for something different here. Hardware problems. I am looking for minimization now. minimize. This one deals with minimization. There's P, a certain computer system decreases immediately after its introduction.
Is the 75 similar to 76?
75 what is the price of the above? Yeah, let's do 75 then. This is the price, and they're asking you to maximize the revenue. The revenue, remember, X times the price, right? Number of items times the price gives you the revenue. So the revenue function here should be X times 24 minus X over 34, right? Distribute your revenue, your multiplication, and get your revenue function. Distribute this, right? So this is this minus X squared over 34, right? Very good. Derivative, set it equal to 0. The derivative is 24 minus 2 coming down, 34 here, X equals 0, right? Solve this, and that should give you the answer, right? So this is not that difficult. 2x over 34, multiplying both sides of the equation by 34, then dividing by 2 will give us the following: 24 times 34 divided by 2, 408. 408, which is there, right? Yeah, 408. Yeah, but then you gotta go with thousands of volts because they are measuring this in thousands of volts, right? You see here, very tricky question here. Thousands of volts, right? Yeah, you follow that, Sarah? Everything okay there? Thousands of volts, 408, right? 1,000. What was that? Everything okay? Thousands of volts.
Yes, Professor.
Yeah, very good, very good. Excellent. All right, great. Yeah, so this was this. This one is actually easy because it's just set the derivative equal to 0, solve for t. That's all, because it's given the function. So this shouldn't be difficult. Let's skip this. Let's go ahead. This one's also set derivative equal to 0, solve for t. I think there was one question that, the GERD, this one we should do. 79, they're asking you to figure out what are the dimensions of this box such that the volume gets maximized, subject to the constraint that the girth plus this length should be fixed, should be equal to 120. Let's do that. Let's label this with X, 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 and X. It's a square, it's stated there. And let's label this with Y, okay? Y, the length. They say that no matter what you do, the girth, which is the sum of these four lengths, for X plus Y, should be equal to 120, right? 120. Very good. From there, we can isolate Y. And the goal is to maximize, maximize the volume, which is the multiplication of the three main dimensions. Look, X height times X width times Y length. Is this X squared Y. We gotta maximize this, right? So from here, subtracting 4X in both sides, you get that 120 minus 4X is Y. That Y must be substituted there, right? That way, you're gonna get your volume as X squared times 120 minus 4X, right? Putting this there. The next is to maximize the volume, right? To maximize the volume. So that's what we're going to do next. So derivative should be set equal to 0. So let's do that. Derivative is going to be what? But before, let's distribute this 120x squared minus 4x cubed, right? 4x cubed. Derivative is 120 times 2, 240x minus 12x squared. That should be set equal to 0. I'm going to factor out x. And I should get this, right? Equal 0. Remember, set each factor equal to 0. This one doesn't make sense, right? So ignore it. But this equation will lead to something that makes sense. Look, 240 equal 12x. Dividing both sides by 12, 20 equal x, right? Aha, this makes sense. This is good. Now, once you have x, then your y, it can be found because y, notice, is 120 minus 4x. But what is x? It's 20. 20 times 4 is 80. 80 taking away from 120 is just 40, right? 40. So y equals 40. In the end, feel free to attach units, inches here, right? 20 inches by 40 inches. So it would be 20 by 20 by 40, right? 20 appears twice. 20 by 20 by 40. So you have the answer there for 79 is this guy, right? 20 by 20 by 40 inches. Very good, guys. Very good. Inches. All right. So moving on. Yeah, we did this. Yeah, this is similar. Someone asked me to do some question. I wonder if I didn't skip. Yeah, we did everything, I think, right? Yeah, very good. Yeah, if not, let me know. Yeah, now we enter into these antiderivatives that we should pay attention to, right? First, take the antiderivative of 3x cubed plus 6x plus 4. Remember, antiderivative behave nicely over sums, over differences. So distribute your antiderivative this way. Antiderivative of 6x dx plus antiderivative 4dx. This antiderivative, once you take the constant outside, is this 3x raised to 3 plus 1, 4. Remember, divided by 4 using the power rule. This antiderivative, once you take 6 out, antiderivative of x raised to 1 is x squared raised over 2. Plus, once you take 4 out, what is left is 1. Antiderivative of 1 is x. Plus a constant, right? Remember, these antiderivatives, they come in families. So simplifying, this should be this. 3x squared plus 4x plus c. So for 82, guys, the answer should be this, right? Very good. Next is similar. It's another polynomial function right there. So let's just skip that one. Yeah, very good, very good. Let's move on. Let's skip the similar. Yeah, very good, very good. So now next, this one. A similar also, right? Polynomial. This one similar, you just have to use this x raised to minus 3 minus x to the third power minus 1 over 7, right? Dx should be fine. This deserves some attention because deals with a trigonometric function. I will explain. What is this? Constant -4. Then you have to integrate or take the antiderivative of cosine of t dt. But what is the antiderivative of cosine of t? Anybody could tell us? Antiderivative.
Sine dt.
Sine. Very good. Excellent, Adriana. Sine, because the derivative of sine, cosine, right? This is some backward thinking that we were doing yesterday. Sine of t plus a constant, right? Plus a constant for 86. So when we get there, 85, 86 should be C. Excellent, excellent. Yeah. Plus a constant because they come in families, right? Very good. This one also kind of a little bit different than the others. Let's just do it quickly. -9 outside, integral of secant squared dx. And what is the integral of secant squared? Anybody could tell us?
Tangent.
Tangent, right? Tangent of x. Excellent, excellent. Yeah, tangent, right? Very good that you have this in mind. But in case you don't remember this, you look at the sheet right here. Antiderivatives, here derivative, right? You will find it there. Antiderivative secant squared is somewhere here. Yes, secant squared, tangent, right? Plus a constant. Very good. Moving on. Moving on, 88, deal with this. We'll explain that sometimes you will be asked to take the antiderivative of product of functions, of two functions, right? And the thing is that there is no product rule for antiderivative, right? No product rule. So we have to turn this into something else and then proceed. That something else is this simplification, trigonometrically speaking. This times this times cotangent, but cotangent in trigonometry is cosine over sine, right? Cosine over sine plus sine multiplying cosecant, but cosecant in trigonometry is 1 over sine, right? Yeah, so I'm not taking any integral yet, no antiderivative, I'm just simplifying. Look, this cancels with this. And as a result, I get that this is antiderivative of cosine plus, it's cancelled with this is 1. Aha, something better to integrate, right? Now, integral of cosine. Integral of cosine is just sine. The integral or antiderivative of 1, just identity function theta, and to make it general, plus a constant, right? Plus a constant. So that's how you deal with this. It's here, 88. Very good, guys. So great. Moving on. We see this other situation. Let me talk about this. What if they ask you to integrate this type of functions, 7e raised to 5x minus 9e to minus x dx? Well, start by distributing the integral, taking outside the constant, you end up with this, right? 5x dx minus, when you take the integral here, 9 constant comes outside, integral of e raised to minus x dx. But how do you integrate this, guys? Remember I gave you yesterday a property. You take this to be itself first, but to counteract the effect of the derivative of the inside function multiplying, you divide by the derivative of the inside function, right? Divide by 5 minus 9 e raised to minus x. Professor, there is no number there. Well, when there is no number, remember there is an invisible one there, right? So divide by -1. And that's it, and add your constant, right? Simplify, you will get here 7/5 of e raised to the 5th raised to 5x minus or minus plus 9e raised to minus x plus a constant, right? This should be it. Yeah, very good, guys. So this will be this guy. Yeah, excellent. Yeah, moving on. This one similar to number 88. Use the trigonometry first and then you do it, okay? Similar to 88. Yeah, use trigonometric transformations first, turn this quotient into a sum and then integrate. Yeah, also I did it yesterday in, I did a similar one in our lecture yesterday, right? Try to check that. This one is similar to the one that we just did, right? Similar to this, similar to 89, similar to 89. This looks different. Let's try this. They're asking you to integrate this to take the antiderivative of this. So that will be equal to what? Antiderivative or integral of this, right? 1 minus x squared dx minus the integral of 8 over x dx. Now, one thing we can do is we can take these constants out, right? That's a property for antiderivative. Well, so we end up with this dx minus 8 out. We end up with this 1 over x dx. Now I'm gonna ask you guys, either from your mind, if you have memorized it, or from the sheet that I gave you, what is this integral? Anybody could tell us? The integral 1 over 1 minus x squared. And as a hint, I want to put this here.
Inverse the sine.
The inverse of sine. Very good, Sarah, right? Look here. Yeah, where is that, Professor? It's here. An integral of 1 over 1 minus x squared is sine inverse plus a constant, right? Sine inverse plus a constant. So, and we said we're going to write just sine inverse. The constant we will consider at the end. Minus 8. What is this integral? Anybody remembers? Integral of 1 over x.
The natural log.
Natural log. Very good, sir. Natural log, right? Integral of 1 over x. Here, natural log of absolute value of x plus a constant. So we're going to write that there. Natural log. To make sure that the inside of the log is positive, mathematicians put this absolute value. And then we add just one constant, right? You don't have to add two constants, just one constant. The sum of two constants is a new constant. So this is it. This is what you should get. Check. Among the choices, you should be good to go. 92. I think it's this one. Very good. Great. Moving on. This one is similar, but perhaps we can do it quickly. Integral of 6x squared plus 1 minus 5 over x. Yeah, it's very similar. Number 6 will come out. Number 5 will come out. We will end up with this. Integral of 1 over x squared plus 1 minus 5 times integral of 1 over x dx. Anyone could tell me what's this integral, the one here? Looking at the sheet or?
Inverse of tangent.
Aha, inverse of tangent. Very good, Ariana, right? Very good. And this one, we just did, right? This one.
Natural log, yeah.
Natural log. Excellent, right? And then in the end, you place a constant to make your solution general. So 93, guys, is just this one. Very good. Very good. Moving on. Let's just be careful here. Let it settle. Yeah, great. Yeah. This one's similar to the one we just did, right? This one's so similar. The initial value problems, right? IVP, not to be confused with BIP. BIP is something different, right? But IVP, initial value problem. Let's do the first one. The first one says, given the velocity and initial position of a body moving along a coordinate line at time t, find the body's position at time t. They give you the velocity, guys, and they give you an extra information. The position function evaluated at 0 is 13. They ask you to figure out what is the position function. All right, so we gotta go back from the velocity to the position function. So you do this by taking the antiderivative or the integral, right, of the velocity, dt. So we're gonna do that. So what is that? Is antiderivative of minus 13t plus 7, right, dt. But what is this? Well, 13 is a constant, comes out as negative 13. Antiderivative of t raised to 1, t squared over 2, right? T squared over 2. And antiderivative of constant function 1 is just identity function t plus a constant. This is my position function. But now, in one hand, they say that if you evaluate your position function at 0, this should give you the following, right? Minus 13 over 2 times 0 squared plus 7 times 0 plus a constant. 0, 0. On the other hand, they are giving you this extra information that this is somehow 13. So make them equal. That will give you the value of your constant 13, right? And we said in this context, right, this physics problems, the constant ends up being precisely this guy, right? So this, and then just put it in the position function and we are done. Then your position function completely determined is this 13 over 2t squared plus 7t plus the constant, but the constant is 13, right? That's it. This is it. So answer for 95 is just this, right? Very good. Moving on. This one is similar, guys. I leave this for you to the completely similar, right? Different initial value, right? But the function is linear. So see, this one probably is someone asked this for this problem. All right, 97, let's see. Suppose the velocity of a body moving along the x-axis is this. Derivative of s with respect to t, the velocity, right, is this guy, 9.8 times t minus 4. Find the body's displacement over the time interval from t2 to t7, given that s is S0 when t is 0. Oh, I see. Yeah, so basically they give you the velocity. They want you to figure out the displacement, right? So we're gonna find the position function integrating the velocity, okay? Yeah, that's what I'm gonna do. Yeah, so integrating the velocity, we get 9.8 is a constant, right? Integral of t raised to 1, t squared over 2, right? Minus 4, constant out. The antiderivative of constant function 1 is the identity function t plus a constant, right? Plus a constant. Now, this in simplified form should be 4.9 t squared minus 4t plus a constant, right? Now, they say at t equals 0, in one hand, at t equals 0, we have this, right? Square minus 4, 0. This disappears. S at 0 is this symbol, S of 0, S0, right? Let's put it there, S0, C. That's the constant, right? Yeah, good. So my function completely determined should be this, right? Completely determined. S equal 4.9 t squared minus 4t plus a constant, but the constant I say is this symbol. Just leave it alone, S0. Now, what they are asking you to do is to compute, S at 7, then compute S at 2, and take the difference, because it says, find the body displacement. Displacement means the difference between the position at 7 and the position at 2, right? So we're going to compute these two, and then take the difference, that's all. So here, this will be this square minus 4 times 7, right? Plus S0. And this should be 4.9, 2 squared minus 4, 2 plus S0. Notice that when you take the difference, this will cancel. So this doesn't matter. So just compute this, and take the difference, okay? So then, therefore, the difference should be what? Well, in the calculator, this difference S of 7 minus, take this in the calculator, this will cancel, right? So we will do it. 4.9. Yeah, so let's use brackets perhaps. Yeah, you can compute it partially, right? I'm gonna just do it in one computation. This times 7 square minus 4 times 7. Yeah, that, don't worry about this S0 because it will cancel, right? Yeah, so don't worry about that. It's the same for both, minus bracket here, 4.9, 2 squared, square, minus 4 times 2, bracket here, right? Yeah, something is missing there. Yeah, let's use parentheses maybe. The computer likes parentheses. Parentheses here, minus 4 times this, parentheses. Yeah. 200.5, right? 200.5, and that should be the answer. 200.5 here. Very good. Yeah, Yeah, do you understand? Adriana, I think, is the one who posted this question, right?
Yes, thank you.
Yeah, it's just the difference of these two numbers because S0 is the same, so they cancel. So
Yeah.
it's 200.5. Yeah, very tricky question. Yeah, but it's just it. All right, great. So now let's try to do at least one of these, 99, 98, 99. let's check this out. Yeah, this is similar than this, so I'm gonna do just 99, right? This will be similar. Here they give you the acceleration is 18, and they want you to compute the velocity, and then the position function. They give you two conditions here, this and this. Right, we're gonna use both. Okay, yeah. So let's do it. First, start by integrating. Yeah, somehow this went away. Yeah, the velocity must be gotten by integrating the acceleration first, right? But the acceleration function is just this, 18 dt. So integrating this, you will get 18 t plus a constant, right? And we call this constant 1 because there are going to be two constants. But now they say that velocity at 0, which is in one hand, this is equal to 3, right? 3. So C1 is 3. This is telling you that your velocity is 18t plus 3, right? Done with the velocity. Now we're going to retrieve the position function by taking the antiderivative of the velocity. So we're going to integrate this guy now, 18t plus 3 dt here. Take the antiderivative. That will be 18 constant. Antiderivative t raised to 1, t raised to the second power divided by 2. Plus 3 is a constant. Antiderivative of the identity function, constant function 1 is the identity function t plus some constant 2. Notice that this simplifies to this. And in one hand, this position function evaluated at 0 should be this. In one hand, right? 0 disappears. Let's call it constant 2, right? And this is 0 that is telling you is 7, right? So C2 is equal to 7. So simply put the C2 in there, and then you can say, okay, then S should be completely determined and equal to this 3t plus 7. Very good, guys. This is 99. This guy, right? Very good. Yeah, probably we should finish up with this, the last question. Yeah, it's also initial value problem, I think, right? They say the velocity is this, but it's tricky. So I'm gonna warn you there. Yeah, B is this, the velocity. They want you to compute the position function by integrating the velocity, right? Or taking the antiderivative of the velocity. And they give you this extra information. So integrating cosine of pi over 2 times t, what do we get? Look, the antiderivative of cosine, we all know is sine, right? Sine of this guy, pi 2 over t. But when you take the derivative, always you have to multiply by the derivative of the inside function, right? Which is this. To counteract that, just like we did with exponentials, this should be divided by pi over 2, right? Whatever this is, you put it in the bottom here. All right, plus a constant. Now, division by a fraction is multiplication by the reciprocal. So I hope you guys will not have difficulty by seeing that this is just this, right? Sine pi over 2t plus a constant. Now, in one hand, they say that S at 0 is written here. I saw it. S at 0 is this, right? Using the function. Sine of pi over 2 times 0 plus a constant, right? Sine of 0 is 0. Yeah, but on the other hand, they say that this guy, S of 0, is 1, right? 1. Sine of 0, 0 times pi over 0 is 0. 0 times 2 over pi is 0. So 0 plus c equal 1 as usual, right? Look, this guy ends up being my constant. So then just put the constant in here and that's it.
Professor, can you please repeat when you do the integral of cosine?
Sure. I will repeat this. Let me just write this down and state the answer and we will repeat this, okay? Yeah, so instead of c is 1, yeah, 1. Yeah, it's a very, I think it's a little bit tricky, so I will write a note here. Yeah, so this will be the last D. Yeah, very good. Yeah, let's repeat. This part, how we got from here to here, right? How we got from here to here, right? Yeah. Okay, but we're gonna use this, okay? A property. Maybe it's better with the property. Look, when you integrate a cosine of some constant multiplying t, what should be this equal to? We are trying to look for a function whose derivative is this, right? And a candidate that comes to mind is this, sine of k times t, right? Sine. But the problem is that when you take the derivative of this guy, this is equal to cosine of k times t, but multiplied by the derivative of the inside function, which is k, right? So basically this part is matching with what we need, right? But there is a k that is bothering us there, right? So because of that, mathematicians said, okay, don't take this function, take instead sine of k times t divided by whatever you see there to counteract this part. So now it will work, right? Look, this cancels and it returns this.
Okay, perfect. Okay.
Yeah, so the integral of this as a property, right? Very good. As a property should be this sine of kt divided by k, right? And plus a constant, right? You follow this? You could probably write this property somewhere.
Yeah, thank you.
Yeah, you're welcome. Yeah, it's just like we did with the exponential. Okay, guys.